So in this session, we will have a look at the descriptors access write byte in detail. So we were talking about protected modes and the use of descriptor in protected mode. We saw the format of the descriptor generically. What we will do in this session is concentrate on the access write byte alone. As we saw in the previous session, a descriptor is going to be 8 bytes and every table has 8192 descriptors in it. Hence the size of the LDT and the GDT would be 64K each. And the descriptor we said has a different format in 80286 and a different format in 386. But any descriptor which is written for 80286 is accessible for 80386 as well. It's upward compatible. So we had a look at the descriptor of 80286. The descriptor has three main data in it. One, of course, is the base address. The second is going to be the size of the segment. And the third is going to be the access rights for that particular segment. It is this access right because of which the mode of operation is called as protected mode of operation. So let's have a look at the descriptor of 80386 as well. In case of 80386, again, the difference between 286 and 386 is in the last 2 bytes of the descriptor, or the most significant bytes of the descriptor. In case of 80386, since the address is going to be 32 bits, the base address B24 to B31 is also available, and the limit size is extended to a 20-bit limit size. And this 20-bit limit size can further be extended by making use of the granularity bit. But what we are interested in this particular session is look at the format of the access write byte. So if we look at the access write byte, this is going to be a 8-bit value. This is going to be byte number 6 in case of 80286 as well as 80386. This is the format of the access write byte. Every bit in this byte has a meaning. The first bit, which is the A bit, is used for indicating whether this segment has been previously accessed or not. If this bit is going to be 0, it means that the segment has not been previously accessed. If this bit is 1, the segment has been previously accessed. The next 3 bits together are used for indicating what is the type of segment you are trying to access. The E, ED/C and R/W. If all of them are going to be 0, it means that the segment that you are trying to access is a data segment, and it is a normally organized data segment where you will be incrementing the address one after the other if you want to access the data bytes. So, and again, if R/W is going to be 0, it means that this data segment is read only. You can read data from that segment, but you cannot write data into it. If this were 001, again it indicates data segment and the addresses are incremented in order to access consecutive bytes, and this also has write permission. So the R/W bit is essentially used for indicating whether write permission is available or not, provided this happens to be the data segment. Now if ED/C bit is going to be 1, this again indicates it's a data segment, but then for accessing the data, the addresses are going to be decremented, the same way as in case of your stack. In a stack, the stack pointer points towards the last address of the stack. And if you want to access data, the stack pointer is going to be decremented. So the data here is going to expand downwards. So this is similar to a stack, but it can be having an option of reading or writing. So if this is going to be 0, then the stack is going to be read only. If it is going to be 011, then you can read as well as write data. So basically the ED/C bit says whether the data is going to be addresses for accessing the address is going to be incremented or it is going to be decremented. If this bit is going to be 0, it is a normal data segment where you access 1 byte of data after the other and the address is going to be incremented. Whereas if it is going to be both ones, in this case, it means that it is going to be a data segment, but then for accessing the data, the addresses would be decremented, the way the stack works. Now, if the E bit is going to be 1, then it means that the segment happens to be the code segment. And if these 2 bits are going to be 0, then it means that you can ignore the descriptor privilege level given in the access write byte, but also this happens to be execute only. Code segments can never be written into. Code segments can be read from. It's also possible that you indicate that a code segment you can only execute, but you cannot read the source byte from it. So this means that there is a code, the code is executed only, it cannot be read by the user. Of course it will be read by the microprocessor, but the user cannot read data from the code segment. So this is an execute only code segment. If it is going to be 101, this is a code segment. Again, you can ignore the value which is present in the descriptor privilege level bits, and here the code can be executed as well as the code can be read by the user. If it is going to be 110, then in that case the value present in the DPL is a valid value. It's a code segment, and since r/w is going to be 0, this code segment is execute only. If it is going to be 111, it is a code segment, and again the DPL values are going to be valid, but here in this case you can execute the code as well as the user can read the code from the code segment. So this is going to be the 3 bits which indicate what is going to be the type of segment, whether it's code or data. If it's data, whether it is normally organized data or it is going to be a stack-like organization, and if it is data, can you read and write from the data segment. If it's going to be a code segment, it indicates the validity of the DPL bit. It also indicates whether the code segment is execute only or you can read some data from the code segment as well. The next bit, which is going to be the S bit, is called as the system descriptor. The system descriptor bit, if it is going to be 1, indicates that the segment is a system segment. Essentially, the operating system also owns some segments in memory. So if it is going to be something which belongs to the operating system or it is going to be used for the routine maintenance of the processor, the S bit will be 1, indicating that the segment belongs to the system type or it belongs to the operating system. So the S bit 1 indicates that the type of segment happens to be a system segment. The next 2 bits are important whenever we are talking about protected mode of operation. The DPL bits give the privilege level of the segment. If the DPL bits happen to be 00, we say that the segment has the highest level of protection. There are 4 levels of protection: 00, 01, 10 and 11. The highest level of protection is 00. The lowest level of protection is going to be 11. So if a segment is given the highest level of protection, if it is going to be 00, it means that only an application which has a privilege level which is going to be equal to 00 can access that segment. If the DPL happens to be 01, in that case, any application which has a privilege level of 01 or 00 can access that segment. If the privilege level put into the descriptor happens to be 10, then any application which has a privilege level greater than 10 or equal to 10 can access it. So 00 is the highest privilege level, 11 is the lowest privilege level. Now since access to the segments is going to be controlled by the privilege level, it automatically means that the memory becomes protected. For instance, any segment which belongs to the operating system will automatically be given the highest level of privilege. So since they have the highest level of privilege, only the operating system is allowed to modify these memory segments. An application program will not be able to access this protected area of memory. So the protection features are mainly implemented using these privilege levels. We'll see more about memory protection when we go to our final module, which is going to be module number 10. There we will be talking about operating systems, memory protection features, etc. Then we will take this up again in detail. Now the next bit, which is going to be the P bit, basically indicates whether this descriptor is going to be valid or not, whether it's pointing towards a valid segment or not. If the P bit is going to be 0, it is not pointing towards a valid segment. If this bit is going to be 1, it is going to be pointing towards a valid segment. So this is going to be the format of the access write byte. The access right byte basically gives a description of the nature of the segment. It also controls access to the segment by making use of the DPL bits. So this is the format of the descriptor, and how this descriptor is going to be used for generating the physical address. We'll talk about that in the next session. So we'll stop here in this session.